All right. So let us at least start with the fifth and sixth experiment. I want all of you to please come and sit this side, maybe possible. All of you, can you sit this side? While doing, are you doing the third experiment till now in your systems? Please sit this side because then the focus will be better for me. Uh, Sir, I need the project working. It's okay. Maybe what you regarding. Yeah. I'll do that. I'll do that. Because A1, A2 together, all together, I'll take it. Sorry for the inconvenience. No, it's okay. No, not. Yeah, the reason I asked you to sit here because once I'll just try to go through the briefing of experiment number 5 and 6 for you. All right. So, and I'm trying to record this session as well so that I can share this with the other people who might be absent today so that they can look into it. So, if you see in your course page already, I think I have uploaded this two materials. So hopefully you have downloaded it. So the first material that will come in is called as the study of call blocking probability versus how it varies with respect to load on a GSM network is continuously increased. If you observe the title is very similar to the experiment number 1 that we did on NetSim, except that we have done in NetSim, but this will be done on MATLAB. This is the first experiment that we are going to do using MATLAB. In this, the primary objective is to implement the Erlang B and Erlang C formula in MATLAB. All right. We are not going to use the MATLAB inbuilt function. There is an inbuilt function on MATLAB with the name Erlang, but we are not going to use that. We are going to use code the direct formula from this side so that we can verify whether the data that we are getting, like data in the sense P, A, and C. If you remember in our theory also, I told you that ideally for any of these, both of these equation, P, A, and C, these are the three components that we need. P is the probability of error, not probability of error, like probability of blocking or probability of delay. A is the intensity and C is the capacity. So this is my intensity and this is my capacity or channel. If you say, I'll not say capacity, but I'll say channel for that matter. That is easier for us. Okay. Now in this experiment also, what we are going to do is we are going to take input from the user about this intensity and channel. All right. That's the first thing that we're going to do. And we are trying to find out what is my probability for the same. Simple as that. That is all the experiment is all about. Okay. Now you can see the two equation that is given over here is primarily a numerator and denominator is where it changes. You can see here it's a to the power c divided by c factorial. Here it is only a to the power c. So the c factorial won't be there. So basically if you have written down one single code for Erlang B, the Erlang C will be just a little bit of change in the numerator or denominator side. That's all. Okay. So that is as far the coding is concerned. Now let me tell you the process that needs to be done. As you can see, it's mentioned over here. So you can see the algorithms or the process which to be done is take input from user for two. You can sit here. You can sit here anywhere. This is single individual experiment. No? So take input from user for two specific parameter, which are number of channels and and the amount of traffic intensity. All right. So this is the first thing that you need to do. You have to take from the user, capture the use from the user, two set of readings. So I'll just try to make a table here for you to understand what exactly is required. This table you need to also prepare while you are doing it for your same. So first thing is number of channel, and this is traffic, and this is probability of call block. Okay. So what you are going to take is first prompt. It will prompt you to give the number of channel. Suppose I give number of channel as 5. See there. Okay. And traffic intensity, first time, suppose I give 3.5 Erlang. It may or may not be part of the table, Erlang B and Erlang C table. That is, for the time being, you sit here. You please sit here. Somewhere you sit. Later on, we can discuss. Okay. So suppose we have the Erlang, so number of channel is 5 and the Erlang is 3.5. For that, you take the prompt, next prompt, it will be again asking you for number of channel. Again, you put number of channel is 5 and you put the Erlang as suppose 2.5. So each channel will have two set of Erlang. The reason is we are going to compare with respect to single channel, that is 5, about two different probability, two different traffic intensity. What is the probability? So you will get some value of X here and some value of Y here. So this is your first set of reading. All right. That's done. Now again, next reading is, so after this you will get a graph. I'll show you the graph. I think if you are referring to the PDF, you will find a final, there is a graph given. I'll explain you that graph also. So this is your first set of reading. Second set, you might increase this to 10. Suppose, just an example, and you take some random value again. Suppose you get 11 Erlang and maybe 15 Erlang. This Erlang's values, you can take any random values. That is the intensity, okay? It may or may not follow your table also. So this can be anything. These values can be anything. So for that, again, if you simulate, you will get some value of maybe alpha and beta. Okay? So basically what we are observing here, we have to take such 5 such readings. So this is my reading number 1, reading number 2, reading number 3, reading number 4, and reading number 5. So total altogether, you should have 10 such readings. Am I clear with this? Because you will see, if you go down the PDF, you will observe that there is a first question itself, you require 10 reading that you need to have. So these are the 10 readings. Each set will have 2 set of readings. So that makes it 10. You just sit for the timing. Okay. We'll disperse. You just sit in any of the systems. We are not implementing anything right now. Right. So is this table okay with everyone? Okay. This is what we are going to do. So now this table needs to be followed for both Erlang B as well as Erlang C. In Erlang C, this PB will be P of B length. That's all. Because both of the case, this is a probability only. So the same process will be adopted for the both. Now, if you see, observe here that in the algorithm, it is mentioned, code the Erlang B. So the first step is take input. So that is done. Second step is code Erlang B formula as per equation. In the PDF, although it is mentioned, it's mentioned already, you can't use inbuilt MATLAB function of Erlang. So please don't do that, because what the problem is, this Erlang formula that you have is the inbuilt function for MATLAB. We don't know what goes inside. Sir, can't see. Okay, so you cannot figure out that what goes inside the formula. So that's why we are ignoring that for the time being. Then you can see the plot and compare the probability of call blocking for different input values. So you take the x-axis as number of channel. Maybe I'll just draw it over here. So this will be my channel and this will be my PB. All right. So this is my channel. So suppose I get 5 channel here. So for that 5, you will get 2 graphs, maybe one here, and the same point you might get another point here. So this might be your X, this might be your Y. Clear with this? So second time it might be a 10, because you have taken 10 over here. So you have alpha and beta. So for example, you might get alpha here, and at the same point you might get a beta over here. Why it is in the same coinciding? Because it is a channel is the same, right? So we are comparing in that way. So you might get a graph like this. So the table and the graph, table you should do it in here in lab. Graph you can generate later and you can attach in the assignment that you're going to submit. Okay. Now you can see verify the, now the last part of it. Now you get this value X, Y, alpha, beta. All right. Now particularly for Erlang B, please make a note of this. For Erlang B, these values of intensity that we have written right now, 3.5, 2.5, 11, 15, whatever we have written, this is absolutely random we have taken. The reason being that in case of your table, if you observe the table, I'll show you the table as well. So if you see the table over here, for example, I go to Erlang B table. This is the Erlang B table, okay? So if you see, suppose I want, just in case, I'll go back to our theory. Suppose 10 channel and 11 Erlang. See this example, 10, and this you understand carefully, okay? 10 channel and 11 Erlang. I'll go to the table, okay? Now let's see. You can see 10 is here, 10 is here. But there is the maximum is 9.68 Erlang that is possible. So if you follow the table, we cannot actually venture out beyond 9.68. But we want to do that. Okay. So that's why we can take any random value of Erlang, but then the problem becomes where to verify that whether the call blocking probability that is calculated is correct or not. How do I check? Because if we had taken 9.68, we can say from the table, it should be 20% of ball blocking probability. But if I take 11 point something, it doesn't have it in the table. So for that, we have another option of doing that. So let me just show you that as well. You go to this website called erlang.com, which will be accessible from your system. Erlang.com. All right. In that, you have online calculators over here. Okay. This is not there in the PDF. Okay. It's not there in the PDF. That's why I ask you to do. Here you have Erlang B calculator. You click on it. It will give you a window of this nature. There can be any other website also, but we are following this because this is comparatively easier. Now in this, you can see the three options are there. Okay, Erlang, blocking and lines. Lines indicates channel. Okay. So what are the two inputs we are taking in this experiment? Channel and intensity. Okay. And we are trying to find blocking. So please click on blocking over here. Okay. Make the use of the second one, which is blocking. Now you put lines as suppose 10 and you put the Erlang as 11. 11 Erlang, just random. You can take anything for that matter. And you go calculate. Now what happens is this website, they will create and they will give you a value 0.261. Okay. Now you have to verify whether the result or the table or the graph that is generated by you, whether it is giving you 0.260 or not. Okay. So that's the verification, because we are taking, this is only for Erlang B's particularly because we have no option in the table given beyond a certain values. So just to explore and venture out, we can take any value. For example, for your case, you take 10 and maybe 50. So what will be the logical explanation? You tell me 10 channels are there and 50 intensity you are looking at. Whether the probability will be higher or lower. Can you tell me just generic way? Whether the call blocking probability will be higher when the number of channels are 10 and Erlang or the intensity is 50. It should be higher because it's a congested scenario. 10 channels, you have 50 Erlangs of traffic. So you can see if you calculate over here, you should be getting around that 0.78, something like that, maybe 0.8. Alright, so this is high probability. So you check it in your MATLAB code also whether you are getting up around that 0.8. You might get 0.798 maybe. So that's fine. Okay. Now this is what you're supposed to do for Erlang B. Is it clear, this part? Alright. Now I'll explain you the graph, how you are going to see it. So if we go down, this is the graph that you are going to obtain for every set of reading. This graph, if you observe, this is for 5 channel scenario. So for 10 channel, you will get a different graph. For 15 channel, 50 channel, whatever the channel you are choosing, based on that, the graph will change. The only thing that you need to note down is the final value that you are getting on these 2 points, A and B. Rest of the values are not required at all. Okay, you get the cursor over here. You will find the value of X and Y, which is mentioned in the box. As you know in MATLAB how it does. You take the cursor over here. It will prompt you the value of X and Y. Note down this value of Y because the Y value is nothing but the grade of service or the call blocking probability. Am I clear with this? Simple. Okay. So for 5 channel, you take the value of A, or rather in our case, whatever the in the table X and Y. So maybe I'll just put it instead of A and B, I'll write it is as X and Y. So this might be my X and this might be my Y. Correct? Similarly, next time you have 10 channels, you will get alpha and beta. For 50 channels with different Erlang set, you will get 2 different values. That's all. That's how you have to fill in the table. And these values should be validated from the website. Am I clear with the instruction? It's okay. Same way for Erlang C also, similar graph will be generated and you have to verify in the same manner. Okay? That's the process is absolutely the same, except the equations is different. But for Erlang C, the problem is if you go back to the website, if I go back to the website and here we have an Erlang C calculator as well. Okay. But if you see in Erlang C calculator as per the website, they are asking for different set of inputs, which we are not taking into account. We are keeping our inputs to be same, intensity and channel. But if you see here, there is no such input possible. So for Erlang C alone, we will follow the table as it is. So it is there in the VTOP. You go here, you take the channel over here, suppose 5, but follow the given intensity. For example, you can take maximum up to 2.85. So you take the first prompt, number of channel 5, give the input as intensity as 2.85. Next prompt, again, asking for number of channel, give as 5, and maybe you give a value of 1.59. Because in those two cases, you know about the probability from the table. Since there is no website that I have found out where intensity and probability can be matched together, we cannot verify for random values of intensity. So let us keep for Erlang C the table that we have for our reference, because it's a standard table. Am I clear? So for Erlang B, verification needs to be done via the website. For Erlang C, the intensity, the values that you are taking over here should match to the results. That's all. It should ideally result. Okay, that's basically what the experiment number 5 is all about. So if you see here as the assignment, they are same. So 10 comparison, everyone clear with 10 comparison? What is the 10 comparison? 5 set of reading, each of them are having 2 sets. So that's why 10 comparison in that way. And then compare it with the bar chart. You can see bar chart or the chart that I told you right now. This graph itself, I was just showing you here. So this kind of a graph that you are supposed to draw, because it will vary based on what you have taken as an input. Third part, you can see here, implement the Erlang C formula. As I said, it will be repeating for Erlang C. Repeat task 1 and 2 for the same. Clear, everyone? This first fifth experiment. Okay? This I want you to finish it off today itself, here in class. Because after some time, I'll even give you the Erlang B code also here, for your reference, for your quick reference, at least to see how the performer should be. Okay. Based on that, you can work out with Erlang C as well. I'll give you after some time. So this is about the fifth experiment. Okay. Any doubt with this? Okay. Clear? Right. Now let us see the second experiment, which I'll explain you now. And hopefully by next week, when you are coming back, you can complete it by that, because that's also relatively simple experiment. One experiment will lead to the others as well. Okay. In the next one. So if we see, this is the next experiment, which is called as MATLAB based comparative analysis between outdoor and indoor propagation model. All right. Now, outdoor propagation model and Okumura and Hata model, we have already discussed in our theory, and this needs to be implemented as given as per the following specifications. So already these are already been taught in your class. So the same specifications has been provided over here. Now, if you observe here, in the mathematical form of Okumura is also presented over here, where LFSL is nothing but the free space path loss. Okay. AMU is nothing but the AMU FD. If you remember in theory, we have done that AMU FD, comma, like this we had written. The same thing is mentioned as AMU over here. HBG and HMG, this stands for GHTE and GHRE. If you remember in theory, we had done something like this, HTE and GHRE. So the same thing is mentioned over here. And this correction is nothing but G area that was there in the experiment, in the main theory. It's just declaration is different. That's all. So this has been mentioned over here as well for your details, for your specification if you want to. Equations are also provided to us. So accordingly, whenever you take the input from the user, it should prompt you to those particular equations, and in order to, and it will try to solve for HMG and HBG. So please make a note of the inputs for Okumura particularly, because you might find it a little confusing at times. So the inputs for Okumura primarily you should take as for the user, from the user, is the distance of separation. I'll tell you why I want this. So first is the distance. Second, height of the transmitter, HTE. Third, height of the receiver, HRE. So this is the third one. And fourth one should be LFSL, which is nothing but the free space path loss. Usually the free space path loss will also have an equation. Okay, as we know, 10 log 4 pi whole square d square y lambda square, but we are avoiding that equation also. If you want to do it, you can use it also, but preferably you can take around 15 dB to 30 dB ka range for this LFSL. You can take this as a direct input from the user. So user will be prompted by 4 things. First, enter the LFSL value. So you take 25 dB. Enter the height of the transmitter, which should lie between this range. So accordingly, in the input statement also, you have to put it that way. Input the height of the receiver also in that statement. And finally, the distance of occurrence, because without that you cannot proceed for any of the calculation, right? So these are the four inputs primarily you will take for Okumura. Now, the thing that is missing over here is the frequency. If you remember in Okumura, the one of the major drawback was that it was more like a based on the graphical representation. All right. So what we are left with is to find AMU and G area. All right. But that depends on the frequency of range. So that's why you define a frequency array which should have around 10 elements. So it means that maybe from 150 megahertz to maybe 1000 megahertz. This is just tentative. Suppose 150 to 1000 megahertz, you take 10 data, 10 frequency values, disjoint values. So you create an array of 10 such values. Why you need to create an array? Because if you observe the graph, if you need to find AMU, this part, AMU of it, you go to this graph. So for those particular values of frequencies over here, you have to take the corresponding value of AMU. For example, I take 150. So it is somewhere in the middle, and I take distance from the user as 50 kilometers. So we go to here. The 50 is somewhere this graph. So I'll go here like this tentatively, and then I go like this in the left hand side, maybe over here. So wherever it intersects, this may be around 38 dB. But this is only for 150 megahertz frequency. Now you have taken maybe 150, after 150 you have taken 200. So you go to 200 here, again 200, it goes here to 50. You come here in the left hand side, maybe it is 40 dB. So can you understand? So you have to declare a AMU array as well, which should also have such 10 elements based on whatever the number of frequencies you have taken. If you have taken 15 set of values of frequency, you have to have 15 values of AMU. Am I clear with this point? Because otherwise there will be dimensional mismatch. The array size won't be same. So it will throw you errors. So if you are taking 15, the more the values are better, because it will give you a better approximated result. But 10 is minimum. You have to take 10 values at least. Otherwise the graph won't be correct. Okay, so at least 10, maximum 15 points is enough. But for all those 15, the AMU array size should be same as that of the frequency array size. Same way, the G area also, if you see, if I go down a little bit, the G area also over here should also have the same things, because that also depends on the frequency that you have chosen. So G area, if I define an array G area, that should also have the same 10 as a dimension of the array, or 15 as the dimension of the array. So for that also, suppose I have 150 megahertz, so I'll go here, and suppose this is open area, so I'll go here to open area, straight line, I come here, so wherever it intersects, approximate value, whatever it is, so 20, 25, suppose I take it as 22 dB. So for 150 dB or 150 megahertz, it is 22 dB. For 200, it might be something else. Maybe I'll go like this. It should be a straight line, although it will come here. So it is around 22.5 dB maybe. Something like that. This approximation is up to you. And we know that this approximation is wrong. That is why Okumura doesn't give us the proper result as such. But that is okay. We will take that as it is. So this is how you have to make this G area as well. So all if you have done correctly, then finally what you have to do is, if I go to the task for Okumura, you can see a graph that plots frequency versus loss for an open area. The first one that if you look at it. So basically you are supposed to get a graph. I'll just give you a tentative graph of it, how it looks like. Usually, it looks like, if you look at this as frequency and this is as loss, whatever the value of frequency, whatever be the range you are taking, more or less the pattern of the graph would look something like this. Okay, more or less. And the smoother it will be based on the number of sample points that you are taking. Okay, tentatively this will be the graph. So this is what you are supposed to plot for frequency versus loss. Same way, rechange the program to make this thing happen for two different other graphs. You can see antenna height versus, that is height of the transmitter antenna versus loss. The second one is receiver antenna height versus loss. And the third one is the comparison of frequency loss versus open, quasi and suburban. That's all. What you're supposed to do in the fourth experiment? Can you tell me what small change you have to make? If you're given the pattern of the first one, frequency versus loss already, what additional you have to do for the fourth one? Anyone? Anyone? Like in this case, we have defined G area, right? So what difference it will make over here? Basically, you have to create two arrays, one with G quasi and the other one will be G suburban. That's all. Rest of the things will be remaining the same, except that there will be three arrays of G area. G area 1, G area 2, G area 3. Maybe area 1 for open, area 2 for quasi open, and area 3 for suburban. So what will happen that you will get three such graph in the single graph. Three comparison. That's all. Okay. And for the 2 and 3, height of the transmitter and height of the receiver, if I go back to the inputs, can anyone suggest me what inputs I'll take if I want to plot between height of the transmitter or suppose height of the transmitter for that matter. Suppose I want to plot height of the transmitter versus loss. What inputs we are going to take from the user? LFSL, fine, because that is generic. We are going to take that. Distance is also fine because we have to fix a distance. Without that, we cannot do it. Distance we cannot vary in each reading because the graphs again will change. So distance will keep constant. So we'll ask from the user. HRE, we are plotting with respect to HT. So HRE also we can ask from the user. HTE, should I ask from the user? We will ask from the user, but in a different way. We will ask actually, you can see here in the first part of it, frequency was a 10 array, right? So that you have to take now as a HT. So you have to take HT as an array of 10 elements. And instead of HTE, you will ask a frequency value from the user. For example, 900 at 900 megahertz with HRE value of 5 meter, maybe with a distance of 50 kilometers, with an LFSL of 15 dB, what will be the nature? So basically, remember one thing, whichever is here as the x-axis, HT or HRE, you have to declare that as an array. Simple as that. That is how you remember. If it is frequency versus loss, frequency will be the array. If it is height of the transmitter versus loss, height of the transmitter will be the array. Okay? So keep the rest of the things to be constant or user dependent. So that is how you are going to make this thing happen. Okay. So that is basically what you are supposed to do for the Okumura experiment. All the four over here. Okay. Now coming to the Hata model, it is even more simpler because you don't need the tabulation as we know from our discussion. So in Hata model, if you observe, the equations are already provided over here. Same process. Take the necessary inputs like D, like FC. Okay, so all these things needs to be there. HTE, HRE, all those things you take it because HRE will be required here. And remember here in Hata model, one of the factor is that whether you are making the measurement under small city or large city. So maybe you can give a case. Press 1 for small city, press 2 for large city. Like that case you can create. Accordingly, the program will switch over to either the first one or the second one. CH is nothing but in the theory that we have discussed as AHRE. It was there in theory as AHRE. Here it is mentioned as CH. Okay. So based on that, you can see here also the same kind of graphs you are supposed to do. Frequency versus loss for small city, everything is mentioned. Comment on the finding, transmitter antenna height versus loss, receiver antenna height versus loss. And last part is Hata versus extended Hata. Extended Hata formula, you get it from the PPT, which I have done in class. It's not there in the PDF. Okay. So it's basically comparison of the two model. So you will get a curve of this nature, maybe of this. So two curve, extended Hata versus Hata model for the same specifications. Right. So this you might do it next week. You don't need to do it right now, or you can do it back home as well. It's MATLAB. So I want all of you to at least complete the task for this one because this will be a simpler way of dealing with it. Please make sure that you finish the Erlang B and Erlang C calculation, verification. Everything should be done by today itself. Okay. Don't waste time. Please carry on. Okay. Any doubt with the two? Any of the two? These two together will be one assignment. Okay, so it's not a separated one. Together you can put one assignment. Okay. All right.